Hi everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And today I've got the pleasure of presenting work from my own group here at the University of Utah. Now, real quick, it's important to point out that although I'm editor-in-chief of the journal, I never obviously handle my own submissions. So special thanks to guest editor Raimundo Arroyave, who stepped in and handled this submission process. Appreciate it. This work comes from obviously my own group, Trupti, Hasan, right? I remember members of my group. But we also had help from members of the School of Computing here at the University of Utah from Vivek Srikumar's group, as well as some colleagues that assisted with the DFT at Ariel University in Israel. Now, this work is entitled CrysText, a generative AI approach for text-conditioned crystal structure generation using LLMs. Now, if you've never heard of that, you probably have heard about crystal structure prediction. After all, we've been doing it for a very long time. And in the last 5 years, this field has moved heavily towards using generative models. GANs, VAEs, diffusion, they've become very popular. But a couple of years ago, something remarkable happened. This paper showed up, right? Published in December of 2024 by Luis Antunes, Keith Butler, Ricardo Gar-Crespo. They showed that you can actually use an autoregressive large language model. It's really like a precursor to today's modern LLMs. But even with this autoregressive transformer, they were able to predict the civ card to predict structures, and it worked pretty well. That was significantly improved upon in later work by Mehta. Here's Nate Groover, corresponding author Zach Ulisi. You can see what they were able to do. They were able to do now fine-tuning with a much larger model and get really pretty great performance out of these language models predicting crystal structures. Which brings us to CrysText, right? CrysText is essentially similar to what we're seeing in those other ones with a few differences. The way that we trained it, the types of models we're using, the way that we're prompting it have some subtle differences. But the key innovation that we're presenting in this paper is the fact that, there are other ways to fine-tune these models. In fact, reinforcement learning is a powerful paradigm. It overcomes a lot of the problems when you don't have simple labeled data that is, a binary yes or no, but rather you have gradients and nuanced ways of rewarding whether something is doing the job you want it to or not. In fact, there's something recently that's come out called Group Relative Policy Optimization, GRPO, which is a clever way of doing this reinforcement learning by introducing a group-based relative reward in the loss function. Let's take a look. First off, CrysText is built off of open source models. We've tried it with Llama 3.18 billion. We also tried it with Mistral 7 billion version 0.3. These were deployed using the Unsloth library. We did QLoRa fine tuning. We've tried both 4-bit as well as 16-bit. These are ways of fine tuning the model that don't use as many computational resources. The dataset that we used initially was the MP20 dataset. That's 45,000 compounds that we can train off where we have the crystal structures. And because these come out of the materials project, they also come with some DFT calculated properties, which means that we can use those in the label to train on as well. What that means is that the LLM is given the instruction, hey, here's the instruction that describes the task paired with an input that provides further context. Your job is to write a response that appropriately completes the request, right? And then the input typical prompt might be something like generate a sieve for a given material description, and then you input the material's composition and the space group. Although you could also do something like generate a sieve that's based off of a description where you provide maybe the energy above the whole. So you're conditioning it to generate materials that are a specific chemistry, specific space group, and maybe even specific materials properties. This first figure shows you the basic architecture we're using, the pre-training models, the QLoRa, how we're bringing in materials, how the prompt input and instructions work, and then the output structures. But where it gets interesting is when you take that original CrysText model and you wrap it in this GRPO reinforcement learning opportunity. Now what happens is that multiple structures get generated, and then what we do is we assign rewards, and this can be totally custom, right? If the civ check doesn't pass, it generates a structure that would violate the civ check. Give it a negative reward. If it's a valid structure, give it a reward. And you can decide what the values should be for these rewards inside your reward function. These are turned into advantages, and that allows you to update the loss function, accounting also for KL divergence so that you don't drift too far from the original training. And ultimately what you get is now alignment, but it's done based off of the group of structures that are generated in these batches. Ultimately, what we're looking for is something like this. If this is what the known ground truth structure is, when we ask it to make the same composition in that same space group, we'd like to see it make the same thing. And then we'd like to measure how far off it was in terms of the RMSE, right? What do we find? We find that it works pretty well. If you look at the match rate, how often did it match within some tolerance factors, right? On the first shot, it's just okay. If you give it up to 19 more, it's getting better and better and better. And if you look at the purple, green, and blue lines, what we're seeing is that reinforcement learning adds a significant improvement to this. It makes it significantly better. It's a clever new way to obviously increase performance while also adding a nuanced and very flexible reward architecture in order for users to align the model to do what they want it to. One last thing I'll mention is that because this is a language model, we actually monkeyed around with the temperature parameter. Remember, the temperature parameter is something, as you change it, it adjusts, it does a transformation on the probabilities of the words that are predicted. So increasing the temperature has the effect of sort of flattening a little bit. It makes it a little more even of a probability landscape for more creative responses. So as you go from light purple to dark purple, you are cooling it down. You're making it more deterministic. And so the structure validity goes up slightly. In other words, you're telling it to give you safer answers, and it is. But we cannot just measure structural validity. We can measure structural uniqueness or novelty, and there's some great tools for how we do that in this paper. And what we see is the opposite trend. As you turn up the temperature, you're allowing it to be more creative, essentially, which means you get more unique structures and more novel structures. So I think this is a really cool tool. It's a great way to generate new structures. It's fast, it's easy to implement. Obviously, the code's available. And it allows you to explore this Pareto front between known materials and interesting new ones while conditioning them on a custom reward architecture, which is really slick. I hope you'll check it out in the latest issue of IMMI.